Welcome back, section 5.5. We're going to spend today working on some of those oldies but goodies, increasing, decreasing intervals, concavity, and extrema. So, increasing, decreasing intervals and concavity, where do they come from? Do you remember? So remembering, did I hear somebody say that? No, I guess not. So increasing, decreasing intervals, that comes from our first derivative test. Concavity comes from the second derivative test. And extrema, remember that comes from our first derivative. And we look at the endpoints of the interval that they're giving us. So those are some of the things that we're going to have to look at and remember. So, can we determine the intervals for which this function is increasing or decreasing? Our function is the natural log of x over x. So the first thing I'm going to do is go ahead and find my first derivative. I have a quotient rule, so I've got x derivative natural log of x, which is 1 over x. To that, we're going to subtract the natural log of x times derivative of the denominator, which is 1, all over x squared. And we'll go ahead and clean this up. So we have 1 minus the natural log of x over x squared. Remember, hopefully, we are going to set this equal to 0 in order to find any critical values. So we're interested in where the numerator is equal to 0 and our denominator is equal to 0. So we've got two things happening here. We have 1 minus natural log of x equal to 0, and we have x squared equal to 0. I'm going to go ahead and solve 1 minus natural log of x equal to 0. I'm going to subtract my 1. So I get the negative natural log of x equals negative 1. So natural log of x equals 1. How do I solve that? We just did exponential equations. Oh yes. Change it to e. Change it to an exponential. So we have e to the first equals x. So x is going to equal e. Here, x squared equals 0, so x is going to equal 0. So it looks like we're going to need another sheet of paper. So we can go ahead and set up our interval charts. So we're going to go ahead and create our intervals about these x values. So we're going to look at 0 and we're going to look at e. Now here's something that you possibly could think about to make your life a little easier. And we'll talk about this either way. Think about the natural log of x. What do you know about the natural log of x and the domain of that? And remember, your pre-calculus teacher might be listening to your thoughts at this point in time. But we should recall that the natural log of x has a domain of 0 to infinity, doesn't it? Doesn't it? Yes, of course. Yeah, your pre-calculus teacher. Great guy. So natural log of x does have a domain from 0 to infinity. So in our intervals, we could start this from 0 and continue up. What happens if we don't remember the domain is from 0 to infinity? Well, we can go ahead then and put in negative infinity to 0 and see what happens. 0 to e, and then e to infinity. All right, so what's the number between negative infinity and 0? Well, I think negative 1 is going to fall in there, isn't it? From 0 to e. Remember, e has a value, 2.71828, blah, 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 blah. So I can go ahead and test maybe 1. And then from e to infinity, I can test 3. So those are my test values. And I'm going to look at the sign of f prime of x, sign. So I plug in negative 1 into my first derivative. And I'm going to guess some of us are going to throw this into our calculator, which is completely fine with me. So 1 minus the natural log of negative 1. If I put the natural log, or if I put this into that 1 minus the natural log of negative 1, it's going to give me a non-real answer. So it's going to tell me to go to that and fix it. So I know that that doesn't work. So it gives us nothing, absolutely nothing, garbage. So again, remember, if I would have started at 0 and continued up, then I wouldn't have had to worry about that. But if I forgot about my domain, then we're going to get something that doesn't work for us anyway. All right, so I'm going to go ahead then, clear that out. So now I'm going to go ahead and do my natural log of 1. So I have 1 minus the natural log of 1, which gives me, that's 1. That's interesting, isn't it? Natural log of 1, remember, is, yes, 0. So 1 minus 0 is going to give us 1. And then 1 divided by 1 squared is 1, so that's going to give us a positive. And if I plug in 3, 1 minus the natural log of 3, natural log of 3 is going to be a negative, or a positive value there. But 1 minus that's going to be a negative value. Yeah, I can do that. Check it out if you need to. So 1 minus the natural log of 3 does give us a negative value. Divided by 9 is still going to be a negative value. So what does that tell me? Well, it tells me we're increasing here on 0 to e, and we're decreasing from e to infinity. So increase on 0 to e, decrease on e to infinity. Now we could take this a step farther as well, and we could call this, well, if we go from increasing to decreasing, we have a relative maximum, don't we? So we have a relative maximum at x equals e, or at the point e, and then we can plug that in to get, if you want, 1 over e. The way I did that was I took the natural log of e over e. Natural log of e is 1 over e. So not that you had to do this part in here, but it is something that we could ask later on, or in sections that we eventually will end up getting to. So that gives us our increasing, decreasing intervals. Next thing we want to do is determine our concavity and any points of inflection for this function that we're given, natural log of x over x. Well, that looks interesting, doesn't it? Natural log of x over x. I just did it here. I must have been thinking. So I know my first derivative is 1 minus the natural log of x over x squared. So my concavity comes from the second derivative. So I'm going to go ahead and find the second derivative of this. Again, I have a quotient rule. So I have x squared, low, d high. Derivative of 1 minus natural log of x is negative 1 over x. From that, I'm going to subtract my high, 1 minus the natural log of x. Denominator derivative is 2x. All over x to the 4th, as that marker starts to run out. So I got a different green one here, maybe it'll help us out. So I'm going to go and clean this up. So we get negative, that's not going to work. Pick another color. So we get negative x here, x squared times negative 1 over x gives us negative x, minus, I'm going to go and multiply my 2x and a negative through, so I get a minus 2x, and then plus 2x natural log of x. And that's going to be divided by x to the 4th. I can go ahead and clean this up as well. So negative x minus 2x gives us a negative 3x, plus 2x natural logs of x over x to the 4th. I can factor out an x out of each of my terms, so I get negative 3 plus 2 natural logs of x over x to the 3rd. Now again, I'm going to set this equal to 0. I'm going to solve each of my numerator and my denominator and set those equal to 0. So I'm going to look at negative 3 plus 2 natural logs of x equals 0. And I have x to the 3rd equals 0. That's the easy one, isn't it? So x will equal 0. Over here, a little more complicated. I'm going to add 3 and divide by 2. So the natural log of x equals 3 halves. Now I'm going to go ahead and change it to an exponential, so change it to e. So e to the 3 halves equals x. And now I can go ahead and set up my intervals. So my intervals in this case, I'm going to go from 0 to e to the 3 halves. Again, I see that my function was the natural log of x, so I know my domain is 0 to infinity. I don't have to worry about any negative values there. So I'm going to go ahead and use that information to make my life a little easier. So my intervals, I'm going from 0 to e to the 3 halves, and then e to the 3 halves to infinity. I need to find some test values. E to the 3 halves, we can go ahead and find a value for that. We can do our second natural log, and then 3 halves, which is 1.5, or 1.5, 1.5. So that's about 4.5 there. So I'm going to go ahead and test 1. That'll be safe. And I'm going to go ahead and test 5. That'll be safe as well. and I'm looking at the sign of my second derivative, SIGN. So if I plug in 1, and again I'm going up here to my second derivative there, so I'm looking at -3 in my calculator. I'm looking at -3 plus 2 natural logs of e to the 3 halves. So I'm going to do my second e to the 1.5. Go ahead and get that. That gives me 0. And then, oh, sorry, I put in the wrong number, didn't I? I was saying that shouldn't have given us 0. Let's go back and do that again. Even I make a little mistake here and there. So -3 plus 2 natural logs of, we're testing 1 there. We're only testing 1. So that gives us -3 divided by 1 to the third, which is going to be a negative. And if I plug in 5, I'm going to get a -3 plus 2 natural logs of 5, which gives me a positive 0.218 divided by a positive 125 is going to be positive. So that tells me we're concave down. All my markers are running out tonight. And then we're concave up. So we're concave down from 0 to e3/2, and e to the 3/2 to infinity, we're concave up. So that's going to tell us that we have a possible point of inflection. Remember, it is only a possible point of inflection because we have to test to make sure it is actually a value. So we're going to find f of e to the 3 halves to make sure it's a point. So in this case, we have the natural log of e to the 3 halves over 3 halves. We can bring this 3 halves to the front. So we have 3 halves. The natural log of e is 1 over 3 halves. Hey, 3 halves divided by 3 halves, that's 1, isn't it? So we do get a point of inflection, POI, at e to the 3 halves and 1. That's my point. All right, and then my very last thing I want to do is find our absolute extrema. We've done absolute extrema again as well. To find the absolute extrema, we're going to find any critical values from x on x over natural log of x. To do that, we're going to find our first derivative. So we have the natural log of x times 1 minus x times 1 over x over the natural log of x squared. X times 1 over x, that's 1. So we have the natural log of x minus 1 over the natural log of x squared. So the natural log of x minus 1 equal to 0. So the natural log of x is going to equal 1. Where does natural log of x equal 1? When x equals e. Here we can set the natural log of x equal to 0 to get our denominator as well. But remember, when does natural log of x equal 0? Well, if we have e to the 0 is going to equal x. And e to the 0 is 1, so we have 1 equals x. We're only on the interval from 2 to 5, so anything that's outside of that interval we can get rid of. In this case, x equals 1 doesn't make sense to us because we're only again on 2 to 5. So we're going to find f of 2, f of e, and f of 5. So in our calculator there, I'm going to go ahead and put this function into my y equals. So I'm going to have x divided by the natural log of x. And I'm going to go ahead and do a table. So second table. And I've got mine already on ask. So I can go ahead and plug in these numbers. So I can plug in my 2. And I get 2.885. I can go ahead and plug in e. To do that, I can do my second. And then my division button is actually just an e. We don't have to do second natural log. Second natural log gives us e to a power. Second division just gives us that e value. And that gives us, oh, look at that. That gives us e, doesn't it? And then 5, plugging in 5, we end up with 3.107. So what do we know? We know that our absolute max is going to be here at f of 5. Again, we can say that the absolute maximum is 3.107, or it occurs when x equals 5, or at the point 5, 3.107. And then our absolute minimum is going to be here at e. Remember, e is 2.7. We had a 2.8 there. So our absolute minimum. Again, we can say that absolute minimum occurs at x equals e. We can say the absolute minimum is e, the y value there, or the absolute minimum occurs at the point e, depending again on how the question is stated. So that gives you an idea of our increasing, decreasing intervals, our concavity, and our absolute extrema. All things we've done in the past, but this time now we're doing them with natural logs. So good luck, enjoy. If you have questions, let me know, and happy finding those derivatives.